So imagine I have a plane in three-dimensional space. And then I have a point in three-dimensional space. One of the questions that you might naturally want to know is like, what is the distance from this plane to this key? Okay, so there's a couple different things you got to think about whenever I say the distance from this plane to this key, because there's a lot of different distances, right? Like the distance from this key to this corner is different from the distance to this corner. So whenever I ask you the distance between a point and a plane in space, I'm talking about the shortest distance, the very shortest distance between the planes and the plane and the point. So the shortest distance between a point and a plane is going to be the length of the line segment that connects them that is actually orthogonal to the plane, right? The shortest line segment connecting these is going to be the one that's orthogonal. So if this is horizontal, then it would be the vertical line segment. Any other line segment that's not vertical would be longer, and so I'm looking for the line segment that's always orthogonal to the plane. Okay, so what we're going to do is say I've got some point, okay, my point is in space is called Q, and then I've got this plane over here. Number one, I'm going to find the coordinates of one point P in the plane. And it doesn't necessarily have to be any particular point. This could be any point. And next we're going to say, well, my vector V is going to be the vector that connects P and Q. So if I draw this vector with its tail at P and its point at Q, this is my vector V. And again, since P was any point in the plane, this vector is not necessarily the shortest vector. It's just any vector with its tail in the plane and its tip at the point Q. Number three is I'm actually going to find the projection of V onto the normal vector. So let's think about why we would want to do that. The normal vector is just any vector that is orthogonal to the plane, meaning it makes a 90-degree angle with the plane in every direction. The reason we're going to do that is because I just said the shortest distance between the plane and the point is the length of a line segment that's orthogonal to the plane. And so if I take any old line segment that connects the point to the plane, and then I think about the projection of that line segment onto an orthogonal vector, that's going to give me the length of the line segment that's orthogonal to the plane and connects the plane to the point. So just to draw another diagram here, if this is my point P in the plane and this is my point Q out in space, and then here is just some old normal vector, taking the projection of this blue vector onto my normal vector N, that projection would look like this. And so that projection is going to give me the distance that I want. And so what I'm doing here is just a little bit of simplifying, right? I said the distance is just going to be the norm of that projection. And so the projection formula is, of course, v dot n over n dot n times the vector n, and I take the norm. Now, a norm is a lot like an absolute value. For one thing, if I have a scalar like this in the parentheses, if I have the scalar inside the norm, I can take it out of the norm. Also, there's a property of norms where if I have a vector like n dot n, right, a vector dot itself, then that's just the norm of that vector squared. And so I can move from this step to this step. And then you can see I've got a norm of n in the numerator and a norm of n in the denominator. So I could actually just cancel one of those. And then really what we're looking at is that vector v, which connects any point in the plane with the point q, dot the normalized normal vector, or you might say the unit normal vector, the unit orthogonal vector, the normalized orthogonal vector. There's a lot of ways to say it. That little hat means that it's been normalized or that it's a unit vector. The hat means it's a unit vector. So if I dot v with a unit vector and then I take the absolute value, again, that's the distance. So that's how I can eventually end up with this formula. So the next formula here is another little leap. But if you're given the equation for a plane in general form, which is this form where you have just that d scalar, then the distance from any point to that plane is given by this equation here. So you can skip all of the normalizing and everything else.
It's just that one, but using the coordinates and applying the rule of dot product. Yeah, exactly. Yeah, I think you guys can probably, if you're interested, just derive this for yourself. Go ahead and, of course, this is general form, but if you want to really explain this to yourself, start with the equation for a plane in standard form. And the equation for a plane in standard form looks like this. That's something you should have memorized. And remember, x naught, y naught, z naught, those are just the coordinates for any point in the plane, any point at all. And remember, a, b, and c are the entries of a normal vector. And it's just the entries of any old normal vector. X naught, y naught, z naught is just the coordinates of any old point in the plane. So if you wanted to go from standard form to general form, what you're doing is you're distributing the a, b, and c, and then you're collecting all of the constants in this d, right? So what is that lowercase d? That would be minus a x naught plus b y naught plus c z naught. So if you apply what we just did with the distance between a point and a plane, and you really consider what the standard form means, you can eventually arrive at this equation, right? Which might be nice to know. It's a little bit shorter of a computation process if you happen to remember this. But if you ever forget this formula, then you can just go ahead and revert back to using this, What's more important for me is that you guys sort of understand the geometric intuition, like you understand how did we come up with this formula. I would rather you remember that. Remember my little explanation about the shortest distance and the projections and blah, blah, blah. I'd rather you remember that than you remember some formula. But whatever works for you guys. So, just a quick example. Let's find the distance between this point and this plane. Now, this plane is almost in general form. If I wanted to write it in general form, I just have to subtract 5 from both sides, and there we go. At this point, I could go back and I could scroll up and I could say, well, let me use this formula, because I know A, B, C, and D, I know X, Y, and Z, to find that distance. But what if I forget that formula? What if I don't remember it? The formula that I do remember is this. And, let me just go ahead and work this process because this is the only thing that I really remember. The first step is I've got to find some point that belongs in this plane. I have to find a point that belongs in the plane. And to find just any old point, I'm going to go ahead and let my x and y coordinates just be 0. And then I'll find what z has to be if I make x and y 0. You have that sort of flexibility. So this would be 3 times 0 minus 0 plus 2z minus 5 equals 0. That tells me that z has to be 5 halves. So the point 0, 0, 5 halves is just any old point, but I know it belongs to this plane. So now for my vector PQ, just any old vector with its tail in the plane and the tip of the vector at the point Q, that vector is going to be 1, 3, and then -4 minus 5 halves. So that would be like minus 6.5, I think. Okay. For my n, remember n is just any vector that is orthogonal to the plane. I can get that from looking at my equation. So this would be my A, this would be my B, and this would be my C. So my n vector is going to be 3. What's my y coordinate, or my y entry? So the second entry of my n vector? -1. And then 2. Okay. Well, that's not normalized yet. N hat has to be a unit vector. And so I would have to find the norm of n, so that would be the square root of 9 plus 1 plus 4 is 14. And so n hat is going to be n divided by the norm of n. And then this dot product is going to be, let's see, 1 times 3 is 3, plus 3 times -1 is -3, plus 2 times -6.5 is -13, and then I have to divide by root of 14, and so this is going to be 13 over root 14 as the distance between that point and the plane, assuming I didn't make any mistakes in there.